are to find all of the zeros of the polynomial p of x equals x cubed plus 8e1x squared. So in this case, we notice first of all that p of 0 equals 0. We also know that we can factor p of x as x cubed, x cubed times x squared plus 81. We can find the zeros of x squared plus 81 by setting it equal to 0, subtracting 81 from both sides, and getting x equals plus or minus the square root of 81 times the square root of negative 1, which equals plus or minus 9i. And so the zeros for p of x are actually 0, 9i, and negative 9i. So when it asks us to completely factor p of x, we have x cubed times, and since 9i is a 0, x minus 9i is a factor, and since negative 9i is a 0, x minus negative 9i is a factor, so x plus 9i. And so this is factored completely. We can see that 0 is a 0 of multiplicity 3, and 9i and negative 9i each have multiplicity 1. There are actually 5 linear factors here for the 5th degree polynomial. So let's go on to the next example. In the next example, we have x to the 4th minus 4x squared minus 5. And we're to find all of the zeros. First of all, in terms of rational zeros, we know that the only possible rational zeros this time are integers, since the leading coefficient is 1. And they are plus and minus 1 and plus and minus 5. We also see that there is one change in sign from positive to negative in p of x. So there is at most one positive real 0. Then we notice that this is an even function, that is, that p of x equals p of the opposite of x. This says that there is exactly one sign change for p of the opposite of x, and so there is at most one negative real 0. So when we look at the graph, and I've already graphed this, notice that neither plus or minus 1 nor plus or minus 5 appears to be a 0. And yet, apparently, we do have one positive and one negative, since subtracting 2 from either of those would make negatives, and that's not possible. So in this case, we will have one positive and one negative irrational number, because the only way we can have real zeros that are not rational, and we've discarded the rational options, is if they are irrational. So in this case, we're kind of at the end of our tools for finding zeros directly, but notice that this is in fact quadratic in form. So we can go ahead and kind of do a roundabout to get our zeros. We can let w equal x squared to get that this is equivalent to w squared minus 4w minus 5 equals 0, which we can factor as w minus 5 times w plus 1 equals 0, which says w equals 5 or w equals negative 1. If we back substitute the x squared for w, get x squared equals 5 or x squared equals negative 1. So here we're going to get x equals plus or minus the square root of 5, and there are our two irrational zeros, one positive and one negative, or x equals plus or minus the square root of negative 1, which is plus or minus I. So we have our zeros, but we came about them by first of all figuring out the factorization. So we have plus or minus square root of 5 and plus or minus I. So those are our options in terms of zeros. The factorization, p of x would equal x minus the square root of 5 times x minus the negative square root of 5, which is x plus the square root of 5, times x minus I times x minus 1I, which is x plus I. Fourth degree polynomial, 4 linear factors over the complex numbers.